Hello and welcome to everybody on Cloud Fitness. So in today's video, we are going to see the practical implementation of SVM kernels. Now, in order to understand this particular video, it is very important that you follow my previous videos, all the previous videos in fact, because until you understand what is machine learning, you will not understand what is linear regression, logistic regression, and if you don't understand those, eventually you'll not be even able to understand SVMs as well. So I do recommend watching all my previous videos in sequence because it is very important. And today we are going to see the practical implementation of SVM kernels. We have already discussed about SVM kernels in our previous videos. So let's proceed today. Now, even before proceeding, I do recommend all of you guys to subscribe to my channel and also connect with me over LinkedIn, and I will leave the link in the description box. So when we talk about SVM kernels, we have seen earlier that for the non-linear data set, right? So if you see, this data set is nothing but it is a non-linear data set, right? If you see, this blue is a class A, and this the red dots is the data set which is of class B, which can be of any other class. Now whenever you're talking about 2D, right, in that case you will not be able to draw a specific line over this particular data set. You will not be able to classify, you will not be able to create a hyperplane on this particular data set. That is why what you need to do is, from 2D plane you basically need to move it to a 3D or a higher plane, right? Now that part is actually done by a SVM kernel, right? So now if you see in this particular plane, right, you have x1, x2 and x3. In the 3D plane, you can apply any formula. So on the same data set, if you apply a formula like, let's say function is like x cube plus 1, right, or x to the power 4 plus 1, something like that, right? Now in that case, what will happen is you will see that there is you will be able to get the difference between these two data sets, and you will be able to classify these two data sets, and you will be able to get the hyperplane in between, what we discussed in our previous video. So this is what your SVM kernel is, because that is nothing but it is a function. It is a function that helps you to achieve this, right? And when you talk about SVM kernel, right, there are multiple types of SVM kernel. So one is a linear kernel. Now this is the simplest kernel, right? It is a simple linear classification in 2D basically, right? Now when you talk about polynomial kernels, right? So polynomial kernel, again, they help you to transform the data into the higher dimensional space using a polynomial function. We are going to see all of this implementation as well today itself. Now similarly, you have something called as radial basis function, RBF kernel, right? And it is also one of the most commonly used kernels as well. So polynomial kernel as well, it is used, basically whenever you talk about polynomial functions, right? So if you see this particular diagram over here, right, if I have these red dots as one data set, right, similarly this green dots is nothing but another data set. So the moment you apply any polynomial function, let's say x square, what will happen is you will get all these points will be plotted somewhere up over here, right? Now the moment this is done, you will see that the green dots are plotted over here, and this yellow line, basically using this yellow line, you can actually differentiate, you can actually create a hyperplane over here to do the classification, right? This is nothing but this is a polynomial kernel. Similarly, you have radial basis function. Similarly, you have sigmoid kernel. Now these are different types of kernel functions. Now do you need to remember the exact the derivation or the exact function? No, you don't need to, but the implementation, you need to put it in your mind. Now similarly, when you talk about formula, now the linear function is nothing but it is a simple y is equals to mx plus c, where you have the hyperplane, and then you also have your marginal planes. Now when you talk about polynomial, right, in the polynomial, this is the formula that is followed. It is same, y is equals to mx plus c, it is the same formula. So basically what happens is, especially in case of polynomial, right, now what happens over here is, for example, here itself, so let's say you have let me in fact show you this particular diagram. Now basically if you see this, right, this is what we discussed, right? The moment you apply any polynomial function, what will happen, the points will be plotted somewhere at the top, and you will be able to get the hyperplane over here, right? Now eventually when you talk about a polynomial function, right, now the polynomial function here, the input is nothing but input is x only, right? Input is x. Now x has two types of x, input is x1 and input is x2. Okay, so there are two basically inputs, which is nothing but x1 and x2. So you have x1 and then you have x2, right? So you have these two inputs. Now x1 is class A and x2 is class B, right? So like that you have two classes. Now when you project these two classes, you will be able to identify the plane over here. Now here what happens is, when you go to another dimension, now instead of x and y, you actually create one more dimension, right? Now when you do that in SVM, what exactly happens is that if you see x1 x2 x1 into x2, so basically you try to do a transpose of these two values over here, right? And from here we basically derive these kinds of formulas. Basically I'm not going into derivation right now, but just giving you an overview. So these are the different formulas which are actually derived, right, for the polynomial, RBF, sigmoids. Now models internally do this, right? So you don't need to remember it, but the thing you need to understand is for the polynomial, right, basically coefficient and this d, right, d is nothing but a dimension, right? So if you are defining the dimension, right, as a 4 dimension, 3 dimension, 5 dimension, right, that is nothing but that is the dimension, right? Now this is gamma. So now what is this gamma? This gamma is nothing but, if I go back to this particular diagram or this particular diagram, so here I have said y is equals to x square. Right now if you want to create more difference, what you can do is you can multiply it by gamma, or you can multiply it by any value. Let's say you multiply it by 10. Now here what is going to happen is, when you multiply it by 10, you know, the scale will increase, right? The scale is going to increase. The moment the scale increases, it is going to help you out in creation of your hyperplane, right? That is nothing but that is the gamma which is present over here, right? Y is equals to mx plus c. C is nothing but c is your coefficient, right? Now if I go back to my sheet over here, right, so this coefficient is nothing but, in y is equals to mx plus c, coefficient is nothing but it is your the same coefficient that you see in the linear regression. Now d is nothing but the dimension, gamma is nothing but it is the multiplier. Now remember that multiplier everywhere, you can see that multiplier is actually happening on this xi, right? Y is equals to mx, right? It is actually happening on mx. You know, all your multipliers are actually happening on your input data set itself, right? Now whenever you talk about polynomial, it directly happens on your input data set. Now when you talk about RBF, it is an exponential increase. So basically here what you are trying to do, from one dimension you are moving to a higher dimension, right? So whenever you do that, what we are going to do, in the first go you are not doing exponential increase, but in RBF you are trying to do exponential increase over here, right? And here you are multiplying it by gamma, but here there is no coefficient and there is no dimension, right? It is an exponential increase. Now similarly when you talk about sigmoid function, it basically is helping you with the tan h function, right? Tan h function also is now your data, the scale of your data is increasing by the tan h function. So if I go ahead and if I say exponential function, right? So now if you see exponential, and if I try to go to the images, so you can actually see how this exponential function behaves, right? Now in the similar case, your data set is actually going to have an exponential growth, right? Whenever you try to do tan h, now let me say tan h function graph. So basically you can see, right, this is the tan h function graph. So like this your data is going to grow. So these are the different formulas that we try to implement, right, as part of your SVM, and eventually this is what we are trying to achieve. From one dimension we are going to the higher dimension. Now these three are the different types, right? These are the different types. Now which one to choose, that is the part of decision making that we have to do, right? And when we talk about SVM kernels, right, so let's see how we can actually implement them. So you can actually see here in the command 1, right, what I'm trying to do, I'm simply trying to, because I have to plot, right? Now here I have to show you in graphical format. That is why from matplot library I'm importing pyplot, right? I'm using NumPy, I'm using sklearn over here. So I'm importing data sets because I'm using one of the data sets from sklearn, and support vector machine because this is what I'm using, right? I'm using support vector machine. So from sklearn I have imported support vector machines. Now similarly, when you talk about iris dataset is one that we have been using throughout our channel, right? So this is the iris dataset. So from the datasets that I have imported from sklearn, I'm using load iris. Now load iris, the moment I do that, I have this class iris. So you can see this is nothing but this is a class. So from this class I'm getting the data and I'm getting the target. So if you see, if you want to see the description, you can simply say iris.description, and this is the description of your iris dataset. So it has total 150 rows, right? It has sepal length, sepal width, petal length, petal width, and class as the dataset. This is the attributes which are present, right? Now in this attributes, basically these are the inputs, and this is the predictions that we want to do, or this is the classification we want to do. Now here, if I try to print the value of x, now what was the x over here? X was my data and y is my target, right? So if you see, this is my x. Now this x is nothing but sepal length, sepal width, petal length, and petal width. And when I try to print y, now y is nothing but the classification. Classification is basically over here. If you go over here, you can actually see this is the class, you know, iris setosa, iris versicolor, iris virginica. These are the 3 types of flowers, right? Now here it is represented in a numerical format, right? This is what we need. So if you see 0, 1 and 2, this is y. Now here, let's, instead of using all the 4 features, we will use 2 features, and we will try to do the classification in two flowers only. So let's do one thing. So what we will do is, so from x we are just removing anything. So basically from the x, if you see over here, we are only taking the first two the first two columns. Basically this is what we are trying to achieve over here. Now when you talk about y, from y we are removing any zeros, right? So from y we are just removing, now this y is nothing but y is the output predictions, right? So I'm just removing these zeros. So I'm just removing one classifier, that one target output. Now this is just a part of the data that I'm trying to collect. Now after doing this, you can actually see that after doing this, x dot shape, so I have 100 records in x, y dot shape, I have 100 rows in y. Now how does my data of x looks like? So this is my data of x. So I have only 2 input features. I'm just randomly using 2 columns over here as my input. And if I show you the y, now you can see that there is no 0 over here. Now this is just the basic you know, the data collection part that we are trying to do. So this is nothing but this is my y. Also you can actually see the total records that I have in x. This is nothing but 100. So I have 100 rows in x and 100 rows in y. And now what I'm trying to do, so now you can see my data is pretty much ordered over here. Now this is a pretty much ordered data. Why it is an ordered data, you can actually see, right? For all the values of my x, it is like the output is very sequential, right? So I don't want my data to be biased, right? To generate an unbiased data, what I'm trying to do, I'm using permutation over here, right? On my data set, what I'm trying to use, data set is nothing but n sample, right? This is my input data set. Now in this input data set, which has 100 rows, I am using permutation, random permutation. So from NumPy, random permutation, I am trying to do a random sampling of the data. So here I am changing the order of the data, right? So seed is 0 here, right? So I hope you understand the usage of the seed. So the moment I try to get the order over here, so this order will remain constant, right? If I have a specific seed value over here, right, the seed will be 0. Now if I run this order n number of times, so I'm going to get the same order. It is not going to change every time with the run, right? It is always going to be 26th row first, then 86th row second, right? So this is nothing but the order of the rows have shuffled. Now if you can see, the moment I have shuffled this order, right, now you can see that my value of x, my value of y. Now whatever the order is, I'm assigning it. I'm saying that take this order and generate my x input feature, take this order and generate my target output as y, and the target output should be float, right? Now you can see, now I have printed x again, so and then I have printed y again. So with the y it will be easier for you. So you can see earlier my y was like 1 1 1 1 continuous and then 2 continuous, right? Now you can see my output has also changed, it has shuffled, right? So it and this has become float. So this is nothing but again the data generation. Now once I've generated the data, right, I am just doing training and testing. Now you can also split this data, right, using train test split, right, but here we are trying to do a little manually. So you can see that here x train, y train, x test, y test, right. So here this is my training data set. I'm generating the sample training data set and testing data set over here, and after that now you can see here I'm generating my SVM models. Now I'm saying I'm generating a for loop for this particular training data set, right. Now you can see for kernel in, so I'm using three techniques over here: linear, RBF and poly, right. So I have explained you over here that linear, RBF and polynomial. So these three I'm using over here, right. Now these three techniques I'm using. Now what I'm saying, svm.svc. Now this is the whole part where I'm defining my support vector machine. Now if you see SVM, right, SVM I have imported at the top, right. If I go at the top, this is where I have imported my SVM from sklearn. Now if I come down back over here, so I'm using this svm.svc, right, to create my model. Now if you want to understand even more detail of this svm.svc, you can anytime go to this particular page of sklearn, right. Here you will see sklearn.svm.svc. so all the parameters are defined over here if you want to know even more detail, right. Now let me show you this. I'll go back over here. So from svm.svc I am defining my kernel. Now this kernel is nothing but what kernel I want to use. I want to use linear, RBF or polynomial. So I'm going to define here. So now since this is a for loop, it will run for each of these three. Gamma is 10 over here that I have defined. Now what is this gamma, right? I've already defined that this is the value of gamma over here that is going to happen, right? This is the value of gamma if you see over here, right. Now again if I go back over here, you can see here I'm training my model. Now I have got my model as CLF. Now CLF.fit x train, y train. So using this x train and y train sample data set that I have generated, what I'm trying to do, I'm going to train my model, and then I'm generating my graph. I'm simply generating my x and y axis, right, and from there onwards I've started. Now this is nothing but this is all I'm using my plotting library. I'm coloring it, you know, I'm trying to generate basically the whole plot over here. You know, after generating the model, I'm just putting it on the plot. So this all is nothing but it is coming under plotting, you know, defining the plotting part. Now once the plotting is done, I'm just saying plot.show, right. So this particular model, this particular command 22, what it is doing, whatever data set you have generated at the top, it is using that data set, and after using that data set, it is trying to use a for loop for each of these kernels, and it is trying to train the model, and it is trying to create the graph. So now this is the graph which is created. So if you see, this is the linear model, this is the RBF, this is the RBF which is generated, and this is the polynomial kernel output which is generated. Now in this whole part where I have plotted, right, I have done multiple things over here, right. I'll explain you through the this particular visual. So if you see this linear, now what I have explained earlier, right, if I go back over here, so this is the linear SVM, right. So you create a hyperplane, you have a positive and negative values, or you have a class A and class B, right. Similarly here you can see this blue is class A, for example, and this red is class B, right. So you have some blue points over here, and similarly you have red points over here, and you also have outliers, right. So I explained you outliers as well. So few blue points are also present over here. So these are nothing but these are the outliers, right. Now all these dots are nothing but these are all training data sets. Now the double dots that you see, this is a test data set, okay. So these blue dots are nothing but these are all training data set that I have derived. Now this is the linear, now this is the hyperplane which is generated, and this is the marginal plane which is there, the dotted line. Now when you talk about RBF, right, so in RBF you can see this is how your plot looks like, right, this is how your plot looks like. Now if you can see your marginal plane, right, and your hyperplane, this hyperplane is your solid black line, and then this is your marginal plane. This is how your RBF looks like. Now this RBF looks a little better than this one, right? Now when you talk about polynomial, right, now this is kind of a polynomial plane that is generated. Now if you see over here, there is a marginal plane. Marginal planes have a very less distance. This is what it looks like. And then you have your your soft planes, soft marginal planes, which have a very less distance, and then you have these outliers as well. So this is basically how your SVM kernels are practically implemented. Now there are a lot of things into it, right? There will be your hyperparameter tuning, your cross validation and everything. We are going to cover it in our next video, but this is just to show you this part of it, right, that how it is implemented. And even this svm.svc, right, so you can provide multiple parameters over here. Now this gamma is also a hyperparameter, right? I already told you here, if I say gamma, coefficient and d, these are all hyperparameters. Now how the parameters are taken, which are over here. Now c, right, the c, if you see the default value, I have not provided any value of c, so by default it has taken 1 as the default value. Now if I do not provide any kernel, right, it is by default going to take it as RBF. If I don't provide any degree, right, it is by default going to take it as 3, right? Now similarly gamma value I have by default, like I have provided it as 10, right? So these are the different parameters that it takes, and if you don't provide any of it, it takes the default value. And what is the default value, you can actually understand automatically. But here the major ones that we use is the c, right? The c I have already shown you, the coefficient, kernel, degree, gamma, right? And then weight class, we are also going to see this class weight as well. So these are the major ones that we actually use. So I hope you like this video, you understood this basically how the linear, RBF and the polynomial is implemented. So you can actually go ahead, try it out as well. And I hope you like this particular video, and do remember to like, share and subscribe, and remember to watch it again in case you don't understand it. And you have to follow this whole series in sequence if you really want to learn this skill set. So thank you so much for being till here.